Hello all, welcome back to Basic Programming on the C64. Now today we are going to be going on to Chapter 7, Introduction to Sprites. Now, fair warning, this is going to be very complex. But before we get to all that, this one might be a bit long too, this video. Before we get to all that, I have a couple how do I say this? I have to make some corrections. That's it. And my in my basic programming, I think it was colors and whatnot, colors of memory. I mentioned that the 6510 was an advanced version of the 6502. Thanks to Mr. Ken Jennings, I realized I was wrong in that sense. The 6510 is basically has a 6502 with bank switching and a few things and some commands for talking to the dataset. Other computers do the same without that very minor modification. The 6510 was the exact same instruction set used in the 6502 in the Apples and Ataris. He also mentioned that, that as I said, in passing, sort of glancing, I said that this, sorry, other way around, or the electrons are going to fall out. This, I said, was an RF shield, or high voltage shield. It's more like after saying that, I realized I was actually speaking kind of weird and I didn't say exactly what I meant. What I said was this was high voltage shield or something like that. What I meant to say was this is an RF shield due to the high voltage components underneath, like the high power rails and stuff like that, and as a heatsink. However, since doing that, I've done a little bit of research, and in fact, this piece of cardboard is actually the RF shield. This is a heatsink, and I'll show you something else right here. Whoops. Let's put this back. Okay. This is a Commodore 64C. Now this one was made in Hong Kong and a few other things. However, this is a huge heatsink. This here, and probably an RF shield. But it's a heatsink because all these little fingers here were pressing down on the chips. You can still see the heat paste, including this one here, which is the VIC chip. Now you can see on the board, hold on, here we are. You can see on the board, you can see there is a footprint for a can there, and it is very much isolated from the rest of the circuitry. But it's more, and you can see there's a huge God Almighty ground plane. But this is the VIC chip, and you can see that the board is different. It's a lot more gold-ish. It's not actual gold, it's just gold-ish color. Yeah, still got all the chips around. See if I can clean this off, because I think this one has a different SID chip on it. No, I'm not going to be able to clean that off. Oh dear. Well, anyway, thank you to Mr. Ken Jennings for pointing that out. Thank you very much. And please don't be afraid to point out my mistakes. I am in no way a professional in this matters. I just did this because I found the manual. And a lot of these things I have just learnt in passing and in history. I love to learn, so if you point out things for me, that'd be fantastic. But of course, every RF module in any electronics has a huge God Almighty can. Because that, by very definition, is producing an RF signal, except it's all being funneled out that instead. But still, Yep, this is the C64C. This is actually the first Commodore my family ever owned. Or Commodore computer my family's ever owned. So, there we are. A little bit of history for you. This one was made in 1986, I believe. Whereas the bread bin one down here was made back in 84. 84, 85. Anyway. Enough of that. Also, while I'm here on this topic, thank you to everyone who has been doing comments for me, like Old School Coder. Thank you so much for the tweet and all that. Thank you. I did get actually a few more subscribers from that, which is really cool. Thank you so much. And thank you for telling me why the cursor didn't start in the middle of the screen. Thank you very much. I did actually realise that at the time I was reading the book and a little light just came out of my head. But I didn't actually say anything. Stupid me. And thank you to Stone of Brathammer, I think your name is. Thank you very much for commenting. ST is C64 time counter. Yeah. Something. There was another comment there, but I think he's since removed it. Because it's not in likely spam or anything like that. Actually, I might have a look at that while I'm here. No spam. Yay! Okay. So, enough of the formalities, whatnot. Let's get into some coding. So, well, I'm going to have to move over a little bit. Oh, yeah. Oh, got off tilter. Have I gone off a little bit? No, I'm fine. Okay, it's just my monitors being silly buggers. Alright. So, we've got sprites here. Now, before we get into this, once again, there is something I have to go over. Now, at the beginning of this chapter, it explains bits and bytes and binary. Now, binary is complicated. My binary math is hopeless because a lot of it is instinct these days. So stuff like that. But so there is a mathematical formula for converting a number to binary, but there is a nice way of doing it. But first, I've got to explain what binary is and how does it relate to machines and whatnot. So we're going to jump over to the old faithful GIMP over here. The GIMP. Now you see, where's my wake up? There we are. Now, you see up this top grid up here, I'll just zoom in, sorry. You see here, we've got, this is base 10, so it's basically, yeah, so where's my pencil? Yeah, okay, so this is base 10. So basically when you write, say, let's change color, let's change it to, say, blue. Okay. Okay, alright. So let's say we want to say 56. So we've got 5 in our 10s, 6 in our 1s. 783. 3 in the 1s, 8 in the 10s, 7 in the 100s. I actually muddled that bit up. Just ignore that 0. And we've got, say, 5,842. So we've got 5 in our thousands, 8 in our hundreds, 4 in our 10s, and 2 in our 1s. However, down the bottom here is a binary table. Now this is commonly referred to as base 2. So base 2. Because there's only 2 possible digits in this, whereas in this there's 10. So I can, technically speaking, go 3, 4, 5, 6, 7, 8, 9, 10. However, in this, in my 1s here, I can only go 0 or 1. So that's what base 10 means. Oh, sorry, got to put a 0. No, not there. Here. 0 to 1, 0 to 10. So basically, every digit is 0 to 10. Whereas in this is only 0 to 1. So there's only 2 possible values in each of your decimal places. Sound complicated, doesn't it? Yeah, I guess. And there is technically, yes, there is base 3, base 4, base 5, base 6, and all that. There's all kinds of different bases, and they do have their special uses. However, for this one, we only need to concern ourselves with this one. So, basically, how do you determine a number into binary? So, let's start with our top one here. Well, we can't do these other ones because I don't go up far enough. So, but what's this? 56. Okay. So, we don't need a 1, we need a 2, because 6 and 4 equals 6. So 1, 1. I don't know after that. Okay, anyway, that will equal 6. Well, let's just do this. I couldn't be bothered doing anything else. Sorry. So 16 and 8 is 32, so go 1. That is 33. So 33. 1, 0, 1, 1, 0, 0. That is 32 plus 8, which is 40, and that is 44. Now there is a very complicated formula for it. Well, not so complicated, I've actually completely forgotten it. I did learn this back in high school when I was doing software design, and I've completely forgotten it. Let's do one more just to make sure. So we've got, let's go 1, 0, 1, 0, 1, 1, 1. So we've got 64 and 16. That is 80. So that's 80, 4, 6, 7. So 87. See? That's how you define a number in binary. Now this is incredibly important. We'll discover that next. Now, hold on, where's my OBS gone? There it is. Now, so it goes through a bunch of stuff and saying how to define binary, what does a binary mean, bits and bytes and all of that mean. Well, we don't need that. There's a binary to decimal conversion, such as here. So basically, you go 2 to the power of whatever decimal place you want, and you'll get that number. There's even a tiny little program down here in BASIC, so you can convert your decimal point into binary, or binary into decimal point. Yeah, but converting binary numbers into the decimal values. So since you're using this program, you should enter and save it. Enter an 8-bit binary number, 8 bits, please. Now, many computers, this is very important. So computers don't deal in halves or quarters and all that. They like to have very even, padded out chunks. So you can't really say 2 bits here, unless you specifically tell it in your instruction set, use these amount of bytes. But generally speaking, a binary number has a length. Like this one has one, this one has one. So technically 56 can be written like that. This, oh sorry, wrong, hold on, bring up GIMP again. So basically, like I've done here, 56 can be written with 2 zeros in front, we just naturally omit them. Same with that. Same thing, 783 can be written like that, we just omit the 0 because it doesn't really mean anything. Unless we put a 1 in front of it, then it does mean something. Or we put a decimal point at the front of it, then it does mean a lot more things. However, with this, I'm going to put a different color, let's go green. For this, binary is the same thing, but in many cases it has to be there because a lot of instruction sets depend solely on the length of the value that you're giving it. So for argument's sake, what we're going to do with the sprites is that. It's what we're going to need, is all this. And it will become apparent soon. And one more. Now, why sprites? Why do we use sprites? Why use sprites in the first place? Well, what are sprites? Well, a sprite is a group of pixels in memory and on screen. So basically they're all pretty much in a container that you can move around like that. Like you put things in a box to move, you put all your books in a box, you put all your toys in a box, and all that, and you pick up the box and you move it around. Imagine if you can just duplicate that box with everything inside of it and just move that around, and move that around, move it around, or in some very technical ways, you can have multiple boxes, but they all point to the same toys or same books. That's another programming thing altogether. But for this case, a sprite is basically a container of pixels with a few tags hanging off it, saying where it is it on or off, what colors does it use, and so on and so forth. Which we'll get straight into. So basically, okay, first things first. I'm going to need another image in the GIMP. So let's make a new one. That's not my pen. This is my pen. Okay, so first of all, now, sprites, like I said, have a tags hanging off it. It's basic, a little attributes pretty much hanging off it. These are called registers. Now, a register is a place in memory, whether it be on the board memory or on chip memory or something like that. It's basically a point of memory that the CPU will read and use the data for what we did before. Like we did with in the last video where we were changing the colors, that memory location is a register for the border. That register, and the other one was a register for text and all that as well. Now, a sprite has quite a few registers here, which I will list right here because we're going to need them. So, register. Now, first of all, these registers. These registers start at the beginning of the VIC chip, which in memory starts at location 5, 3, 2, 4, 8. Now, the VIC-2 chip can handle up to 8 sprites. Now, 8 sprites, so it has a bunch of list of objects going down like that, sort of thing. Bunch of containers. Now, here's a tricky bit that a lot of your coders don't understand a lot of times, is that these sprites are what's called zero indexed. In other words, this top one here, which is this first one here, if you want to know where it is in index, like what's it identify, where is it in the list, not naturally you assume this is 1, so like that. See, you say it's 1, then this is 2 and 3 and blah blah. Actually, that's wrong. In programming, when you're having a list of things, generally speaking, unless you're told otherwise, so it's safe to assume, all lists in programming all start at 0. So that's 0, 1, 2, 3, 4. Okay? Okay, sorry, I have to cover a lot of things in this, because this also comes back in a minute when we actually get to coding. So basically, back to the registers. This is our base memory location, so that's our base memory. From there, from that point, if we go plus 0 to 15, that is the sprite position, so S position. So putting a value in between these variables here sets its position. 16.16 is extra movement, so extra movement, don't know what that is. 21 is enable, whether it's on or off. If that sprite is on and off, and 23. 23 is expand, so essentially expand vertically. So vertical, say scale. 27 equals priority. Now priority, I'll do a brief demonstration of, so let's bring this up a little bit. Red. Let's make another layer. So basically, say that's a one sprite right there. I'm going to make another layer. Let's change the color to orange. Let's make another sprite like there. So priority means which one of these sprites is on top of the other. So a priority like that, or I could put this one as a lower priority or higher priority, whichever way it wants me to be. Okay, so let's bring this back. So that's what sprite priority is. Now, one of the benefits of sprites is sprite collision, which we won't be handling here. Basically, it has hardware-driven collisions, so it detects when one pixel of a sprite has hit the other pixel of another sprite. Now, one real good reason for doing sprites is ease of use. So like last time when we were doing the bouncy ball thing, we were literally moving a character to different spots, basically redrawing the entire screen time and time again. With sprites, you don't have to do that. You have one little shape that you can move around the screen, and you're not constantly redrawing it over and over and over, because memory access time builds up immensely. And not to mention, what the method we were using before is CPU driven, whereas sprites are hardware driven on the VIC2 chip. They're handled hardware like that, which gives a lot more time for the CPU to do things. So basically, the VIC2 can handle 8 sprites on screen, except with tricks you can actually get more. So basically, it's safe to assume it's 8 sprites per line. So per vertical line of pixels, you can have 8 sprites. Okay, so the next priority, next ones is 20. Get on the right layer. There we go. Next one is 28, which is the color mode. So multi. Oh, I'm a programmer. We don't spell. Color mode. So basically, the multicolor mode. So basically, sprites have 2 color modes, so basically, each sprite has a grid of say 8 things. I'll just do that many, however. So you have a pixel here, a pixel here, and a pixel here. However, because of that, you can only have 4 colors per 8 pixels. Because of binary reasons, you can only have 4 colors. However, with the other multicolor mode, I can't remember what it's called. You can have more colors. You can have up to 8 per 8 pixels. However, each color will take up 2 pixels. So it'll be like that. It'll be like that. And it'll be like that. That's why in some Commodore 64 games you see the sprites are the characters, and like the characters, especially like my video on Great Gianna Sisters, you see Gianna's quite stretched out horizontally a little bit. That is because they're using this mode, so the pixels are become 2 pixels wide. Alright, it's complicated. But we won't be doing that today, unfortunately, because we won't have time to do all this. So this sprite video will be 2 parts, unfortunately. So, 29. It is going to be horizontal scaling. So, horizontal scale. So the size of it horizontally, whereas this one is the size of it vertically. But you don't really set in a size per se. You take a base image and then you scale it up. You stretch it up and out. And it works. Then we've got the last ones here. 37 equals what colors you're going to use. 37 to 38 is your colors, your base multicolors. Oh, damn it. This up a little bit. There we go. Let's get rid of this. I screwed that all up big time. Okay, let's go back. Okay, so what is it? Again, it is 37 to 38 is multicolors. Hey, I spelled it right. Oh, no, I didn't. I missed it now. Ah! So basically it defines what the colors you're actually using. Now, it works like a palette, essentially. You define what is the palette of this sprite. And then when you're defining your sprites, you use certain numbers, certain places to define colors. The latest one, that's in normal mode. The next one is 39 to 46 equals your color. Basically these here. You define a palette for that mode where you got long pixels. Now how this all works is you start off with this thing and then you go, that's the definition, that is the points of for the first sprite. Then you go on from here. So then you, for the second sprite, you loop this over again and add again. So add 0 to 15 and you'll get your, so from there on, so let's go say 47 to 15, which is 61. We'll be defining its position. We'll be defining the position of sprite 2 of the next sprite in the list. So basically we define this one, then we move on to that one. So basically it starts from here and you keep working your way down your list. Okay, designing the sprite. Now this is tricky. Basically a sprite, it says here, a sprite is made up of, hold on, I'll bring this over a bit. Let's bring back to my lovely mug. Okay, we got a sprite is made up of 504 dots. These are arranged in a 24 dot wide by 21 dot deep. So a grid down. Actually, what I will do, I'll be right back. Coming back, I actually brought myself a grid book for this. This is how many things were designed for games and programming and whatnot back then, was using grid books like this. Now this is not big enough for what we need, so basically what it's saying is we need 24 wide, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. Okay, so I've only got 16 across here, which is enough for 2 of these, so actually, so go 16 across, so 16 and 1, 2, 3, 4, 5, 6, 7, 8 to there. So we'll go across to this one. Then it's what, 21 down. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20, 21. Alright. So basically we go from there down to there and across like so, and down like so. Pen's not really working. I don't know if you can see it, but you can see I have made a square here, basically going all the way up the top and down here. So basically each square in here is your pixels. Now I have gotten a better example of this, which I'll show right now. So basically I'm just showing you this, so when you see the next image, you know what to see. What I'm actually seeing. So, put that over there. So we're going to have to go back to the GIMP again. Stop it again. And we've got over here, we have a little sprite I've designed, a little fox. So what it does is, so you have 24 dots across, 21 down. Now I've done it like this because the grid doesn't line up anymore and all this. So basically I did this at really small scales with a grid on and just plonked little squares in. So basically this is it. And so imagine like lines going down like that, and like that. One there, one there, sort of thing. So basically each of these have been defined by these numbers. So what you do to define a sprite is all these grids going across like that. For each of these lines, work out the decimal value for all your pixels in each of these. And you put them in groups of 3. Since this top row has no pixels, so therefore it's 0, 0, 0. Whoop. What's happened here? I think I scaled it up a bit too much. So, I'll select, no, there we go. So, 0. Okay. So, for the next one, we got 64, because that's the only sprite, that's the only pixel on that line, so 64. And the next one, a lot more complicated, I'm going to need the calc. This one. Calculator. So basically what we do, we go reading from right to left. That's how all binary numbers, like you do in normal numbers, read them from right to left. So basically we've got no one, so we've got 2. So sorry, where's my mouse? So it's 2, 4. Oh, back hole. So it's 2 plus 4 plus 8 plus 16 plus 32 plus 64. This is where all those numbers come from, like 128, 116, and all this, blah, 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 all these other crazy numbers. So basically, the second one is 126. So 1, 2, 6, and then we have this one over here, which has no pixels except for the 1 and 2. So 2. So you do this for lines going down, 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 down until you got all your numbers. Okay. So basically, that's how you define your sprites. You define by, use your binary numbers, like a filled in pixel is a 1 number. It's basically 1. And all these blank ones, which will be 0, and is treated as transparent, so the background will show through. Okay, so a sprite has transparencies compared to like drawing all the screens with colors all the time, where you got to work out what's color behind and all this. Sprites have transparency, so if it's 0, it's transparent and it doesn't get displayed, and you go boop, boop. There we go. So now you understand why I had to do all this binary stuff at the beginning, because that's how we define our sprites, and how we've got to define where they live, where they all are, and how we do these things. So basically, in this book, they have a sprite already designed for me. So let's go back to me. We have here in the book, I'll bring it over here a little bit. There, okay. So basically we've got a sprite being designed, which is a Commodore balloon. It explains down here how to interpret it. There we go. So you can see it's got 3 columns going down, 3 sets of numbers, and you've got to work out what those numbers are as it is. And with that, we can finally get to some coding. Where are we at? Oh, geez, like 36 minutes in, and we're only getting to the coding. Sorry about all this, but I had to define, or I had to explain all this stuff at the start. Otherwise, jumping into these without knowing what these numbers mean, what all these values mean, doesn't help matters. So let's get into some Commodore 64. First, I'm going to have a drink. Alright, let's get into the nitty gritty with my C64 emulator sort of thing, because my C64s are fried. So let's get to typing. I don't need my Wacom anymore. Oh yes I do. No, I don't need the Wacom anymore. Let's move you over here. Over there. There we go. Terribly sorry about all this. Not very professional, but you all know me. So let's start. Well, we'll go new. Make sure we've got clear memory. And we'll go with this. So done. RAM up. As you all remember, RAM is a remark and is thusly ignored. Now, I'm sure you see here that it's all in capital letters, all the text. Well, that was a limitation of the C64. Not print. Okay, move you over a little bit. There we go. So let me keep all across. There we go. So print. Yeah, it's all in lowercase letters because that's what you can only display one or the other. It could not display both at the same time, unfortunately, which was weird. So that's delete. Control home. There we are. That will clear the screen. Okay. So 10. V equals 53248. So basically, this is the start of the display chip or the VIC-2 chip, which was an improvement over the VIC-1 in the VIC-20 machine. It was all weird names. Which just the VIC just means video interface chip, like SID, the same thing, sound interface device. Okay, so this next bit is a little bit complicated. So 12 poke 2042, 13. So basically what we're doing, this bit is telling us where the sprite will be stored. The actual pixel data itself will be stored in memory. So this is what's called a sprite pointer. It's basically, in coding languages, especially in C, C# and all that, a pointer is basically just a variable that's just pointing to a place in memory. It's just pointing to a memory address. That's all it's doing. Or memory address or a bunch of memory, as in the case with this. So the sprite pointer indicates where you have stored your sprite in memory. The sprite pointers are stored in 8 bytes from location 2040 to 2047 inclusive. So basically all 8 sprites. Normal location of the normal location of the pointer for sprite 0, which is the first sprite, is 2040. Okay. The location for pointer of sprite 1 is 2041, so on and so forth. So like I said before, where all the indices are 0 indexed, like I said over here, like I said here, so 2040 is 0, 2041 is this one, so it starts at 0 and works its way up, and ends at 2047, which is sprite 8. So 8 minus 1 is 7. Okay, let's get back to the C64 stuff. Okay, cool. So basically we're saying point it at this sprite. This sprite we want to point to the 13th block. Okay, so on is used for location. Each sprite pointer can contain a value between 0 and 255. This number multiplied by 64 corresponds to the start address of your sprite data. Since each sprite uses 64 bytes, the sprite pointer can contain a block number anywhere within the first 16K block of memory accessible by the VIC-2 chip, i.e. 256 by 64. It is also possible to use other 64K blocks. Further details can be found in the Commodore 64 Programmer's Reference Guide. Note, it is always advisable to store data at the first sprite block of your first sprite at block 255, and then store data for subsequent sprites in the next available blocks, working downwards. This will prevent your sprite data from interfering with the basic program, because then you'll be writing your data to where the basic is actually stored, or where your program is actually being stored. You know how if I press enter now, it will be stored in memory. If I do list, it'll bring it up. However, if I exceed my bounds, do a little bit, store it in memory, run it, then go list, you'll see my program would be all weird and just wouldn't work. So basically, you must store this in the next available 16K block of the memory. Blah, blah, blah. In the balloon program, line 10, which is the 5528, yep, assigns a value to the start address of the VIC-2 chip in the variable V. Later in the program, you can add the register number to the address stored in V. For example, poke V214 references line 21. The line 12 on the boot, places data for Sprite 2 and block, So basically, we're storing our data for Sprite 2 in block 13. That's all we're doing. The 13th 16K block. Okay? Understand? Good. Hopefully you do. So next line. Okay, just regular stuff. So 4. Oh, hang on. Get 20. 4 n equals 0 to 62. Read Q. And take that value. Now, so poke 832 plus n to, and put Q in it. Whoop, I didn't miss that. I missed n here. N, comma, Q. There we go, and then we go next. Whoop, next. So basically, this 832 is basically oh yes, is this 13 here times it by 64, and we start off with this, which is 0. So 8320, and then we're working our way up from there, and we're putting this will come apparent later on, because this is we reading our sprite data and we're putting it in this address. So basically telling the VIC-2 saying, here it is, from here, add this, boom, that's what we got. That's where I was going to be. Why, I have no idea for this program. That's probably what he was using at the time. Doesn't really explain why you have to use 13. But anyway, it's just there. 30 for x equals 0 to 200. So for the next 200 steps, we do 40. Poke V plus 4. So basically, as we remember from our list, I'll show you in a sec. this will be, so what's our list of registers? So basically, okay, from our list of registers here, you can see 4 is what we used here, which is start of this. I'm not sure exactly what, but the 4th column is, we are putting data into Sprite 2, by the way. So go back to the Commodore for a tick, show you something. You see here, 2042, we're using Sprite 2 in other words. That's what we're doing, using Sprite 2. Why does my cursor on there look so weird? Anyway, from here we're using Sprite 2. Now, in the GIMP, so we've got 4. So 0, 1 and 2 is X, Y and some other one. X, Y, Z, usually. I'm not sure why there would be Z in this. Anyway. Then 3 and 4. Now hang on a minute. It says here 4 is... Okay, 4 is the X coordinates for Sprite 2. And 5 is the Y coordinate for... So basically... okay. I was actually wrong. I was actually very wrong. Excuse me. I have to get rid of this line. Okay. There we go. I think I'm wrong. Maybe I'm not wrong. I don't know. Yeah, I think it might be. Anyway, I am not sure right now what these values are, but basically register 4 for hold on. So basically register 4 for the Sprite is, well, register 4 is the X coordinates for, yeah, register 4 is X coordinates for Sprite 2. Why? I have no idea. Hopefully someone will point out in the comments why. Because I have been looking over this book for a couple of weeks, which is why this has taken so long, unfortunately. Just trying to figure out why this is, so I can actually teach, but I don't know. Anyway, 50. As we saw in the previous videos, they tend to leave a few things out, and not much use in some cases. So I'm going to put X into the Y coordinates. So it's going to go to top, it's going to go wee, flying down that way. Okay, so we go 60, next, X, 70, go to 30, 30. So basically this is our whole program. It's just going to go like that, and it's going to loop through values like that from 0 to 200. It's going to go down 200 pixels like that, and do its little thing, then go back again and repeat the whole thing. So you see here, we've put our Sprite into memory here, but we're not putting it in memory again. We only have it in memory once, and we only need it there. So as we're going through this, we're just moving the Sprite down, because the Sprite's already in memory, and all we have to do, instead of rebuilding the Sprite, just move it. Put it back, move it, put it back, put it back. So where is the Sprite data? Well, that's what I'm going to be doing now. This is a lot of it, so I might make a few errors in here. So 200, huge jump there, isn't it? Data 0, 1, 2, 7, 0. So basically that's 1 pixel. As we look up, should be. Oh, it is. Yep. So hold on. I'm going to bring me up again. Oh, hang on. Put me up here. Just scale me up a little bit. There we go. So basically, as you see in his, if you can actually read it. Sorry, I'll bring it really close. Okay. So over this side, back to so basically we've got 0 because there's no pixels on that top line. Then we go across 127 because we've got the pixels in there, which are add up to 127 in binary, and the none on the other end. So you can see what's happening here. We're defining 1 block, 2 blocks, 3 blocks in those 3 numbers, rather than putting out all the ones and zeros yourself, which you kind of have to do in assembly. I don't know. I might do a video on that after I've done all these things. So I'll just move myself back there. Okay, turn me off. Okay, so let's keep going. So 1, 2, 5, 5, 1, 9, 2, 3, 2, 5, 5, 2, 2, 4. Wasn't typing in the right window. Wonderful. So, yep, still recording. Good. 0, 1, 2, 3, 5. 1, 9, 2. Now, this is how a lot of the early games for these machines were made. It was because of this programming of BASIC and loading things in out of memory all the time is what fueled the bedroom coder boom of the 80s. And certainly in the UK, because you had the ZX81s, or ZX80, ZX81s, and of course the big one, the ZX Spectrum. Now they were a lot more to the metal compared to what I'm doing here. They didn't really have any helper functions or stuff like that. You had to literally put everything into memory and hope for the best. But what also fueled them is what I'm doing here. I'm reading from a book. A lot of the magazines at the time would print out programs for you to type into your Sinclair or your home computer at the time. So, but unfortunately, a lot of those had errors in them. Some printers and printing typos. So a lot of the coding was done troubleshooting these programs to see what actually was a misprint, what actually didn't work. But because of this printing of programs and stuff like that, a lot of the kids at the time thought, hey, I've got a cool program, I'm going to send it in and see if they'll print it. And a lot of times they did. And because of this, some video game publishers started taking notice. They're going, hey kid, how about we distribute your program for you, your game for you and all this. You code the games for us and we'll distribute it for you and we'll give you a little bit of a penny for it. This is how really good, interesting games came about, was because these were kids. They were literally kids and they're just making games of everything they thought they could. Now at the time, and because of this fantastic culture of free expression and free creativity, a lot of the paradigms of games we see today and stuff like that were born out of the experimentation of these kids in their bedrooms in the early 80s. Or late 70s, early 80s, I should say. And out of this we had things like Manic Miner and Jet Set Willy, which is really cool. And even the big behemoth of Elite was done in this exact same way. It was done by a kid pretty much in his bedroom on a BBC Micro, no less. Which is absolutely astonishing to get that sort of stuff out of the BBC Micro, but hey, it's cool. So, a lot of people claim that America was the birthplace of video games and all this, which is technically true with Atari and Electronic Arts sort of thing. But it was the British and Europeans who refined it and made it into the art form that it is today, really. They were the pioneers, especially with studios like of course, one of my favorites of System 3. What's it? Imagine Ultimate Play the game. Ultimate, which later became Rare, was a bunch of kids in their room. Was the two Stamper brothers, and they made some really cool games. Back on the Spectrum. I can't really stress how much I feel that without the Europeans, without England and all these kids, we wouldn't have video games today, because the crash happened. And yeah, so basically what I keep trying to say is that when you had the early video game crash of the early 80s, that only happened in the US. But when you watch a American documentary of video games, it says, oh, it's a worldwide phenomenon and all this. No, it's actually strictly US. Because over in Europe and England and all that, and even in Australia, we took the bull by the horns. We embraced the micros to their full potential. Well. Alright, so we've got this typed in. That's enough of a rant, I should say. Well, we got all this program typed in. I probably typed in a few typos in there, maybe. I don't know. But I got all my line numbers. Yes, just want to go through. So, okay. List, just to make sure. Up, and away. Yep, print that. V was that. Poke. So if I run this, we should see the C64 balloon float from here down to here. So let's run and see what we get. Nothing. Absolutely nothing. Alright, let's see, what did I miss? Okay, someone's probably screaming at me right now. Okay. So print up, so that's done that. 10. What the hell? Why is that a 12 there? Should be. Oh, I missed the goddamn line. We didn't enable the bloody sprite. Okay, I missed a goddamn whole friggin' line. Okay, 11. How did I do this? How did I miss that? Poke. 3 plus 21. 4. Now this 4, as we so basically, hold on. First of all, 21. If we go back to our stuff here, or even go to the book here. See, 21, as you can see there, is enable on and off. Now we're passing in the value of 4. Why 4? Why can't it be just 1 or 2 or something like that? There's a reason for that. Now this gets a little bit, well, cool and inventive. So now, we've got our binaries here. Binary number. Here's 4. There's a 1 there. So if I go back to me thing here, hold on. Go back to this. So basically if I do 0, 1, 0, 0, you can see here Sprite 1, Sprite 2. Boom. There. So basically we're doing the third index sprite, which is still Sprite 2, because 0, 1, and 2. Okay, because if we see over here, there's 0 indexed. So it's actually the third one in. Understand? So that's what that 4 means. So if I put 2 in there, it will be this one. If I put 1 in there, it will be this. If I put 8 in there, it will be this. You also notice that 4, 2, 1 equal up to 7. They don't equal to 8. Which is pretty cool. Alright, so So you understand. So like 21, we turn it on. We put the data into this, and it's 4, which is Sprite 1. And then I can put this one in here. It'll be enable Sprite. What was it? 4, 5, 6, and 7 and 8. Yep, there we go. So that's how you enable your separate sprites. So we go back here. Let's finish up me coding. Alright. Was it number 11? Yep. Yeah, it says here, remark, enable Sprite 2. Okay. So if I press enter on here, it will be put into memory. So if I go back to the list, as we saw in the first episode, you'll see line 11's there, and we have now enabled the sprite. So let's run it. It's there, and see, there we go. We've got our little sprite moving all the way down there. Whee, whee. So if everything should be fine. So let's turn the sprites on. Sprite colors. A sprite can be any number of... Oh! Hold on. List. Okay. No, that's something else. Okay, so never mind. A sprite can be any of 16 colors available on the Commodore 64. The colors are numbered 0 to 15. Contains colors and the codes. As you can see from the VIC2 register map, the Sprites has its own color register. Register numbers 39 to 46 are used for this purpose. Register 39 holds the color for Sprite 0. Register 40 holds the color for Sprite 1. And so on with Register 46 holding color for Sprite 7. When you see your sprite on the screen, the dots are displayed in the color contained within the color register. The rest of the sprite is transparent and shows whatever color is behind the sprite. If you wanted to change the color for Sprite 2 to light green, code number 13, simply poke your color code as follows. So let's try that. So we've got a bit of space up here, so we've got 13. So let's put in. So 13 poke V plus 41, 13. Okay, so let's list, just to make sure we've got that all right. Do you know right? Yeah, go. All right. So if I run this, it should now change color. Yeah, see, look. Got a different color sprite. Because I put a different value into a different register. Which is really cool. Okay, so here we go. Sprite positioning. Okay. Now you've made a sprite, you want it to appear to move around the screen. To do this, your Commodore 64 uses 3 positioning registers. A sprite, X positioning register, sprite Y positioning register, and C, most significant X position register. Okay, the X and Y position registers work together to pinpoint where your sprite appears on the screen. The X position register positions the sprite in the horizontal direction, and the Y position register positions the sprite in the vertical direction. On the VIC2 chip register map, notice that registers 0 to 15 are used for X and Y coordinates. These registers are arranged in pairs as follows. Register 0 holds X coordinates for 0. Register 1 holds Y coordinates for sprite 0. So what I was getting confused on before, as it seems, so list. So as I was getting confused on here, for arranged in pair, I forgot my 0 indexed. Okay, so 0, 1 holds the sprite position, the X position for sprite 0. 2, 3 hold for sprite 1. And 3 and 4 and 5 hold it for sprite 2, which is what we are doing now. So if we go from up to 16, the sprite registers, which as said before, as we go back to the GIMP for tech, as we see here, we've got 15. So basically 0, so it's basically 1 to 16. So 16 divided by 2 is 8. So you can get 8 sprite positions into there. So X and Y positions. And because it's 0 index, we've got a 0 to 15. So it's complicated and it's really annoying at times. Yeah. But anyway, it's one of the really cool, interesting of coding. It's one of those things. Let's go back to the command. Yeah, we've still got a balloon floating there. The pattern is repeated for register. Okay. There's a further register 16, which I shall discuss later. You can position the sprite by poking the values into appropriate registers. You know both X and Y coordinates to position your sprite. Calculate your positions from the top left of the sprite area. Does not matter how many dots you fill up in the area allocated to your sprite design. The position will be calculated from the top left corner. Okay, uses the for next loop to move it down. So as this goes up to 200, x. So there we go. So if I was to quickly change that, so go say 30, x equals 0 to, I don't know, 256. Oops. God damn it. For x equals 0 to 256. Let's see for what we'll get. Moves down even further. Illegal quantity error M40. Okay, so we've gone a little bit too far. So let's back up to say 250. Let's see what we get with that. So we'll go 30 once again for x equals 0 to 250. So we'll get with that. Just go run. It's up there. There we go. So now it's going through the entire screen. Hey, that's cool. And of course we can use complicated mathematics of saying how high the sprite is and not going further than that and all this other thing. Okay, so what's this? You may have noticed that when the program is running, the balloon did not move to the far right hand of the screen. Positioning the horizontal direction is difficult since you need 320 locations and therefore need an additional bit, which will then give you up to 512 positions. If you do not understand how we arrived at this figure, think of the extra bit added to the left hand side of a byte. This would be the equivalent of 2 raised to the power of 8. The extra bits in all sprites are stored in the most significant bit register, MSB, register 16. Bits 0 to 7 of this register correspond to sprites 0 to 7 respectively. If you are not using positions greater than 255, the corresponding extra bit position must be turned off, i.e. it must contain the value of 0. Here's how SMB works. After you've moved the sprite to X location 255, poke the sprite's decimal value into register 16. For example, to move sprite 6 in horizontal sprite 6 to horizontal location 256 through to 320, use the statement poke v 16 v plus 16 64. So in other words, we are putting the value of 64 into register 16, which is weird. Well, anyway, let's try a different color first of all before I go anywhere. List. It was 13 with the color, wasn't it? So 13 poke v plus 41 to change the color. Let's go say, I don't know, 5. See what we get. Run. get a duck green. Okay, with the balloon floating about, I say we're going to have to leave it there. We've got expanded sprites coming up next, and stuff, and a few other sprite priorities, creating more than one sprite and turning sprites off, stuff like that. So that will be the next video, which will show. Hopefully, it will be a bit shorter than this one. I did go on a long bit, but you have to understand I had to explain that. Otherwise, a lot of these things would not have made any sense. And for all those who know all this, I'm terribly sorry that you had to sit through my terrible explanation of it and didn't get into the nitty gritty, which was only a little bit of coding, really. So, did a little bit of experiment with it, and so on and so forth. So, I hope you enjoyed this little video on using sprites in the Commodore 64, and I hope to see you soon. Keep the comments coming, of course. I'm more than happy to have them. Thumbs up and all that. You know all that nonsense. Subscribe and all that. And once again, thank you, and I'll see you all next time. Bye-bye.